Morty, we've got to turn the project in early.
Oh no, I'm gone. Ah! How you doing, Blake? How you doing, Shaq? Didn't know I had vanished right there. Juliana, good to see you. What are people working on? A little chill music while we get started right here. Let's get in some coffee. Woo, busy morning. Busy morning as we are 1 week away from Thanksgiving. Thanksgiving holiday, Tara, good to see you here. What do we want to work on? Some Pearson, some 320, some false 74, some decision trees. What should we look on? What should we do? What work shall we do? We are actually talking about right now in the background the responses to the technology survey. So if you did the technology survey, check my comps roll. I feel like is really off. Yeah, do you want to put your numbers in the chat? I can run it right here. We were doing some work on the technology survey and doing the analysis of all the responses from the students. So if you gave your responses, huge shout outs there. Piano. We'll have some more piano later in semester. We should do more piano. More piano. I need all the coffee. We don't have to do it, but can we look over the data analytics time for the... Let me pull that up again here. We did that last time, so I might do a quick overview of it, but Shaq, good question right there. Let me open the license for jump for the 15th time. Okay. My license has been accepted. Piat, what margin of error are you getting? What do you get for your margin of error? What do you get for your margin of error? Piat is... What do you get for your margin of error? About what percent? What do you have for your margin of error? Your margin of error calculation. Yeah, that looks about right. It's about what I'm getting right here. And then what's your upper bound on your interval? This is not the exact answers, but what's your upper bound? That looks about right. And then what's your lower bound? Yep. Yeah. Looking right. Great job. Oh, did you already do the calculations, Blake? Here, watch this. We can do it right here. So this right here, let's get, so P hat is this, Q hat is 1 minus P hat, and then standard error P hat is equal to P hat times Q hat over N. N is equal to 250. Oh, well, we stored N. Then square root, which we can do SQRT before this. There's the standard error. Z is equal to 1.96 for 95% confidence. And I didn't do the save into arrow. And margin of error is thus equal to Z times standard error of P hat. And so margin of error is that right there. And then P hat, we could make the interval of P hat minus margin of error, P hat plus margin of error right there. There we go. Yeah, and this should do it. We could times this by 100, and then we could take the interval right here and round it to 2 decimals. So there we go. That should be what you're getting right there. 60, there we go, 60.2. And you're rounding it to 1 decimal, right? There we go. And so what we could literally do right here, watch this. Watch this. This is a little crossover between classes right here. Let's say paste your interval is, and then let's put this as interval. So let's go here to interval, store as interval, and put this right here as interval. Your interval is, oh wait, we don't want that. Your interval is this to Now let me show you the magic of this. Are you ready? Your interval is blank to blank, okay? So do you see all this right here? You ready? We take all of this code right here, and with this code, we make a function. In the function, we call make interval. So let's say make prop interval. Make prop interval is going to take nothing. It's going to do read line, and read line is going to say, what is your sample size? And right here. And we will do as.numeric, and store into n. We're going to take our previous code right here, and then we are going to say, what is your successes? And I think that's all we need on them. How many successes are there? Oh, we'll say, what is your p hat? Because we did with p hat. So what is your p hat and sample portion? P hat right there, and then that's all we need. And p hat, we won't have it change the confidence level, but now we could advance this by doing more cool stuff. But with this right here, I think that's got everything, because we could change what the Z star is. But you ready for this, Blake? Now watch this. Make prop interval. So for Tara's question right there, it says, what is your sample size? So Tara said their sample size was 250. What is your sample proportion? Tara said 0.54. There's your interval. So we could go right here and go to the city ballot initiative, do the same question. Where is that on the homework or the... Is that on the homework or the... Which one is that on, Tara? Is that the homework or the quiz? The power of coding. Little stat tool on Hacker Man right there. Let's go here and look at it. Was that on the homework or the quiz? Environmental group, Oceana? Yeah. Take a look at the Oceana one. Which one did Tara say? City group or something, right? The quiz? The quiz. So we'll take a look at that other question right here in a second too. So this is the environmental. Might be able to cheat with this on the other one too. So many questions. So remind me, if you see the Oceana one, mark it. This is the city ballot. Number 14, I'm going to write that in the chat right here so we find it again real quick. Oh my gosh, so many questions. Here it is. So 53 of... Wait. Oh, because they're doing 2 intervals. So they want for both these intervals, the first interval right here is 54% with 540. So we could literally run it. So 540, 50. Oh, careful. We could just move the decimals. 54% or 540 is the sample size. 554. There it is. Oh, we can't move the decimals. So there it is right there. My second is that. Watch this. There you go. Does this help with the work? So all I'm doing right here, Tara, is what? That's Tara. It's Tara. All I'm doing is what? Is I'm just solving the work right here, finding the standard error, using the z-score. Now, I don't have it set so I can change it from 95% confidence. I could write the code to change that. I would have to use the normal curve to find the values and plug that in and put default 95% confidence. Let me do that really quick, then we'll change questions. But hopefully, Tara, that's helping you out with this one. I'm going to do more standardized. This is more BAS474 coding. So the Z, if I want to actually find that. So with the last part of the question, what would the answer be? So take a look at the last part and think it over. Emily, good to see you here. We're going to do some more traditional. It is helping good. So the Z star is going to be found via the Q norm. Q norm for that's 95. Okay, there's the Z star for it. So we need to find the positive. So it's going to be this. 2 seconds here. I'm just coding this and we're going to do a more traditional way of learning. That's the Q norm we want, so I have to express that by putting in 95. So that is 1 minus 0.95. That's 0.05. That's 1/2 of it. That's 1 minus. That might just be some craziness right there. Okay, that does work, I think. Does. Okay. So then this is conf level, and so conf. What is your confidence level? Just what is your level of confidence? Okay, that should do it. And now the function should ask those three things. And so you say, what is your sample size? Tara said 1500. What is your proportion? And then what is your confidence level? And it gives you the interval right there. So now the function will actually change. We could change it to a different confidence since I wrote it so that it'll take the value and find the proper z-score. You're not meant to know this kind of stuff. Last thing before I go to more traditional questions, the next one we have is the Oceana that we're going to do, and we're going to do it step by step by step. How do we find the z-scores? If it's a 98% confident, my function's going to do that for us. How would we find the z-score for 98% confidence? You will not be doing it this way. How would you find this? And David has it right there. And what does David M. Lane give you for this? So go ahead and find it on the David M. Lane just to show how you can get the z-score for a 98%. My function's doing it for me. So go ahead and see if you can find that for 1,000 points right now to know how to get the z-score for a 98% confidence. What does the David M. Lane say? It only reports it to, I know how many decimals it reports it to. But what does it say? 2.326. Great job, Tara, right there. Tara, you are doing a great job. Let me go and actually just answer that last question for you. Thank you so much, Tara. So if people are wondering how Tara got that, click the second button right here. Type in 98%. And then go here to the between, and that's the z-score for the 98% confidence. Like I said, this function is doing it for me, and it's a function I wrote that someone could then just put in the values of their sample size, their proportion, and their confidence, and it just tells you the interval for the answer right there. So I figured out, Tara, great job. I'm throwing you 10,000 points. You're doing a great job on this. I love it. I want to push people's brains to figure this out. I want to be like, think about how it works, and I'm writing a solver function. So I'm cheating right here. I'm writing my own function to solve the answers for me. So great work. Congratulations, Tara. Let's do the Oceana question. Okay, let me mark this right here. Let's get that Oceana question going. Okay. Stat 201, Chapter 13 quiz. Oceana group. How's it set again? It's number 14. We found it. And number 14 right here. There it is right there. And we're good to go. Here we go. No cheating. I'm sorry, Blake. I'm sorry, Blake. The environmental group Oceana analyzed. What are we going to notice immediately right here? What are you noticing immediately about this question? First thing you think is I need to start marking my what? Channel that inner Leo right there. Notation.
Notation, brother.
Thank you. I think it's which one who says notation in our chat? Is that Ali says notation? Shouts to Ali right there. So notation. You got to know that notation. So what is 1215? What is 1215? What's 1215? That's their sample size. They found that 33.3 were mislabeled. What's that? So is something mislabeled? Is it not mislabeled? Is something mislabeled? Is it not mislabeled? That's a categorical question. Was it mislabeled? And I know that's a number. You might say, well, that's quantitative. That is p hat. Great job there, Blake. So that is p hat. You say, but Brian, that's a number. How's it categorical? We're looking at this package and we're saying, is this package mislabeled? And then we're reporting the percent that were mislabeled. Like, yes, no, we're mislabeled. So was something mislabeled, and we do meet the success failure condition because there's like 800 successes in the sample, 800 failures rather. Great job, Blake, right there. Close, and it's probably not going to hurt us. Blake, you're basically right. I'm gonna throw you some points, Blake. You're basically right. Kind of right. Basically. 7. Yep. Basically right. So creating 95% confidence. Since we are using not p-value, excuse me. Since we're using proportions, we're going to use z's. And so that's going to tell us, and just like, great job, Blake, the z star, which means we pick it based on percent confidence. So the z star right there is 1.96. And there it is. These are all the values. We're good to go. We got our p. And then let's change this here to q. I don't know. Purple letterable right there. Our sample size. There we go. Color coded and good to go. So it really comes down to just plug in 2.65. Is that the margin of error? Thank you, Blake. I think Blake's solving the margin of error. That sounds like to me. This component is known as the standard error of p hat right here. This component is the confidence level or the critical value. Both of these components together make the margin of error. The center right here is the estimate, and these components are going to make our interval right here for us. So let's go ahead and find the interval by putting in 1.96 for the z-score, and then putting in square root 0.33 times 0. It's the weirdest zero I've ever seen. Over. And that's the margin of error. We're going to solve that. And then there we go right there. There we go. Okay, so Blake, I think, has the margin of error expressed as a percentage. So let's go ahead and find this out. Times 0.667. There we go. I like to do this right here where I copy the number and I do 1 minus just to check my Q hat. And then I multiply, divide by 1215. Then square root. Do not forget the square root. It's going to be a little bit bigger than this. When you square root a decimal, it gets bigger because you're undoing the multiplication by square rooting it. So square root, not square, excuse me. So square root and then times by 1.96. And that is the standard error. And Blake is correct. And Blake's already getting that interval right there. Great job, Blake and Tara. So 2.65, we can times it by 100 to get the percent, 2.65. And then 33.3 plus or minus, and that's going to do it. Amazing work. Great job. I feel, Blake was saying easy peasy on this chapter. Are people feeling better about this chapter? This is we're going to do a lot of similar work for the remainder of the semester with confidence intervals, with interpreting them to say, I am 95% confident the true proportion of mislabeled packages of seafood is contained in the interval 30.65 to 35.95. So what are we trying to estimate right here? The true proportion of mislabeled seafood packages. So if someone claimed a third of chapter, yeah, of course, Julia, definitely. So I am 95% confident the true proportion of mislabeled seafood packages is contained in the interval 30.65 to 35.95. Remember, and I don't think we have the interpretations open from yesterday, remember how to write your interpretations. They are key to your understanding. Even though my Pearson always gives you the written version right here, know how to write this out. So was it 30.65 right there to 1 decimal? 30.6 right there to 30. Blake's right there. 30. Oof. Blake, what's it round up to? So plus 2.65 plus 2.65. Oh my gosh. Is it 36? It rounds up, does it? It's so close. I think it does, right? I think it does round up. Yeah, I think it's 36 too. We'll find out. And we could use our cheat program right here to cheat. We're a little cheat program right here. So make confidence interval is 1215. And then p hat is equal to 0.333. Confidence level is 95%. Ooh, wait. Blake, we're seeing something different right here. Did I enter something in the wrong way? That's where I get scared. Let's check our math. I'm a little scared right here, Blake. Or did I might change something about the function. Can't be scared. Don't be scared. We all confirmed the answer a moment ago. Ooh, I don't like this. I don't like that showing that. Scary, right? I'm wondering if something's wrong with my function. Proportion. Well, we all got the same answer, right? Let me look at the math again. 0.33. Let's see here. 3, 1, 1 minus there, divided by 1215, square root times 1.96. Wait, what'd I do? Something different happened. 0.33, 1 minus this times this, divided by 1215, square root times 1.96. There it is right there. And so that is the margin of error. And I don't know why my function is showing a different value over here now, because it's supposed to do the exact same mathematics we're doing. And the confidence level, I didn't change something right there, right? Let me just put this back to, I feel like that might have messed up the function. Okay. 1215. What? Well, it's supposed to do the exact same mathematics. Yeah, again, the same margin of error. I'm just like, how are we? Well, let me go look at one last thing right here. I don't like it when things come out differently. Okay, so our p hat, here's our sample size of 1215. Here's our p hat of this. And so the standard error is equal to that. Z-score is equal to this. Okay, well, I don't know what's going on with the function. Let's not worry about that then. And so we could actually check our work one last time. We were just worried about everything working out perfectly. And there's the interval 30.6 to 36. And that's what we entered in. So all that, so it is 30.6 apparently. Probably has a little wiggle room on that. And what does this confidence interval say? We are 95% confident that the interval contains the true proportion of all seafood that is misclassified. So we are 95% confident, and I like to say I am 95% confident that the interval contains the true proportion of seafood that is misclassified, is contained in the interval blank to blank. Is the government criticism valid? They said the sample size is too small. As long as this sample is what, it's fine to estimate the truth. As long as this sample is what, which we would assume a random sample is this. I am 95% confident the true portion of mislabeled seafood. Boom, Blake, that's worth some 10,000 points. That's practice for the test. Blake has literally put, I'm going to pin it right here, the interpretation like we would write it on the test with the 4 components like you're doing for the data analytics assignment, which we covered yesterday. I think someone also wanted us to cover it today, but as long as it meets all the conditions, we're good. And then we can say that the interval properly estimates what the truth might be. So Blake, great job right there. As long, is there criticism valid? No. As long as we meet all the conditions, then the information could be generalized. I think we're good on a little plus or minus on this. Let's see if we had entered in 0.7 here, if it would have liked it. It would have liked it. If we had entered in 35.9, it would have liked it. I don't know why my function broke, but there is a little wiggle room on those because I was like, I think it has a 0.1 wiggle room. Hey, Simone, good to see you here. If you got any questions, let us know. We're just doing some 201 currently. But yeah, this right here, great question, good practice. I don't know why my function is... What? Blake, what broke about my function right here? What broke? Wait, Blake, do you know what broke? Here it is right here. Do you know what I'm not doing? I'm using the same Q hat I've been using. So the reason the function is not working is because Q hat needs to be solved for. So now... So let me go back in time and bring back the whole figuring out the confidence. So there could have been, I double check those other things I told you. Q hat is 1 minus P hat. And so that was the problem, is the Q hat was not being resolved for. So the Q hat was being used from the global environment Q hat. So now we go back here, we rerun our make prop. Sample size was 112, that right? And then sample size this, confidence level 0.95, and there's the interval right there. So 30.7 to 35.9. 30.7 to 35.9. Check answers, 100%. And so that's really great because we were to regenerate this problem right here. So now it says, well, it's the same numbers. What fun is that? But a lot of these problems right now we could solve using our solver program because I think we have it. So you see it says 15 out of 30. So think about this question right here, which is very similar. Here we'll do this one currently, and let's look at it a little bit more quickly and think about what we're trying to estimate. So once again, we are trying to estimate what with this problem right here. What are we trying to estimate with this problem? What are we trying to estimate with this problem? It's very similar to the last one we just did with a consumer advocacy group looking at mislabeled packages of red snapper. What are we trying to estimate? Good to see you, Priya. The true proportion of mislabeled packages for this type of seafood. Does that make sense? Like, we're going to say I am 95% confident is at 95 that the true proportion of mislabeled seafood packages is contained in the interval blank to blank. Are the conditions satisfied? Condition 1 for a confidence interval is always what? Say it with me. You know it. What is condition 1? Get those points. Random. So did we take random packages or did we just take like the first 30 off the shelf? That would be a convenience sample. That would be bad. Condition 2 is the 30 packages of red snapper that we bought are what? Now you can see what the condition is, but then try to explain to me in full. Ban bias. The 30 packages of red snapper that we took need to be what? This is a weird one. Like, it's like why? It deals with error when it comes to oversampling. So it's weird because more sample is better, creates less error, less uncertainty. Has to be Meath, good to see you here. We want to sample less than 10% of the population. And then the last condition, can you tell me the numeric values to check the success failure condition? The success failure condition will be checked numerically for the confidence interval via the mathematics NP hat and NQ hat greater than or equal to 10. But NP hat, what is NP hat equal to? How to interpret the total number of donations? Yeah, total number of donations and age. Yeah. Interpret coefficients and multiple regressions. Some money, we can do that. So what is NP hat equal to? What is NP hat equal to? Yeah, Blake's rocking out. Great job. NP hat is actually equal to what? Mathematically speaking, NP hat is equal to what? And you can solve NP hat. You can look at N, which is 30, and P hat, which is 0.5. NP hat is equal to what mathematically? We're reviewing the conditions right now for making a confidence roll. So N was equal to 30, P hat was equal to 0.5, because X was equal to 15. So NP hat is mathematically equal to, look how this looks right here. NP hat is equal to what? Just look at the mathematics of it and think what NP hat mathematically solves out to. Because N is number and P hat is it's equal to X. So do you have X is right here in the equation? There's X right there. If you have 15 successes, how many failures do you have? So we have 15 successes. How many failures do we have? If there's 15 successes in our sample, how many failures are there? 15 were mislabeled, so how many were properly labeled? Well, that's P hat, Q hat. And 15 is the amount of failures. So there's at least 10 successes, at least 10 failures. Does that make sense? Because if there's 15 successes, there's 15 failures, and P hat and Q hat are 0.5 respectively. So with that, we meet all the conditions. There's at least 10 successes, at least 10 failures. Yes, because it's a random sample. The sample's less than 10% of the population. There's at least 10 successes, at least 10 failures. Now, what's interesting is the center of this interval is really easy to calculate. What is the very center of this interval, Blake, which you've already kind of calculated right here? We'll write down this in notation format. Value like 15. Well, yeah, there is one that you have to do to calculate the sample size. Good question right there. X is equal to 15. N is equal to 30. Z is equal to 1.96. We're doing this one a little bit differently, kind of writing down the things. I like to mix it up a little bit sometimes. It's like different type of workout right here. So, Colin, good to see you here. Pixie dust for everybody. Have a magical weekend. Let's throw some points for Colin swinging by and saying, hey, Colin, thank you. Colin, I am so glad you always swing by. Colin, if you didn't know it, Colin has been on the Haslam billboards around UT. So shouts to Colin right there. Took the class 4 or 5 years ago, 201. I took it while on an intern, a lot of good stuff. Colin is a celebrity, one of our Stats One celebrities. So always good to see Colin here. And thank you so much. You bring so much positivity. I love it. So with this right here, what is p hat? Who knows what p hat is? How do we find p hat? If 15 out of 30 packages were mislabeled, it's 0.5, right? So x over n equals p hat. It's just the proportion in the sample that is what we're looking at. So so that is equal to 15 over 30. And so this is going to equal to 0.5. Now, what's interesting is I could take some guesses at this. I want to show you what I'm going to do right here. This is a really small sample. So do you think it's going to have a small margin of error or a large margin of error? If you have a very small sample, do you think it'll have a large or small margin of error? Very small sample. So think about your uncertainty. Just think kind of, if you only took a little bit of data, would you be more, it's going to have a large margin of error, right? So smaller sample leads to a larger margin of error. Larger sample leads to smaller margin of error. So that's kind of an important concept. I'm reviewing some of the concepts right here to talk about if you increase n, you decrease, or vice versa. If you decrease n, you increase your margin of error. Because we'd be explaining more. There'd be more observations to understand the data, and you'd have less uncertainty in your data, like in your, I guess your findings. So I could actually take a guess at this. We're going to take a guess just to see how close we are. And if the lower bound for this is 0.390, where is the upper bound? Or I'll even make it even easier. If the lower bound is 0.400, where would the upper bound be? This is a great theory question. If the lower bound is 0.400, where would the upper bound be? And the answer to find this is just theoretical, I'm not saying it's the answer, lies in knowing what p hat is. Because p hat is the center of the interval. So if the lower bound is 0.4000, the upper bound would logically be what? So this is just, that's not the, boom, Blake, you're seeing it, because Blake, what do you know now? Blake, yes, Blake, this is the advanced knowledge. Blake, this is an advanced understanding of it. Because Blake, what have you found? What are you thinking of when you look at this right here? You're able to think of the what right now. And I'll draw out probably what Blake is thinking about. Here's what I think Blake's seeing it. This p hat is the center of the interval. Blake knows that the lower bound is equal to 0.400 right there, and the center is equal to 0.5000. Blake, what can you find out right here? What is that highlighted portion that I'm showing you? And this is just theory right here. This is not necessarily the answer. What is that value I'm highlighting right there? That distance from the center of the interval, which is p hat is the center, down to the lower is a what? That is the what. Because you can use that same distance to find this up here, and that would be the upper. What distance is that highlighted right there? That half the length of the interval is known as the what? Well, so what do we call this half length of the interval right here? This half length, not n, is called the what of an interval. So from the center down to the lower, to the center to the upper, this is known as the what. Here, I'll give you a hint. It's known as the what? I'll give you an even better hint. The margin of error. So the margin of error looks to be plus 0.100 minus 0.100. The interval is symmetric. So using these values right here, or knowing the distance to the lower from the center, you could calculate that. Now, once again, we just kind of did a fake solve on this. We need to go and put in the actual values to solve this out. So if you're watching this and you're like, well, what would the actual answer be? Let's put in our value of p hat, z, and all these values that we have previously. The z is 1.96 for 95% confidence. The David M. Lane can help us find that. It'll be given to us on the test, 0.5 for p hat and q hat respectively. The sample size was 30, and the p hat right here is 0.5. And once again, this was a guesstimate and a theory question on how to solve this. And we'll do Simone's question here next. So 0.5 times 0.5 divided by 30, square root. And oof, it's going to be bigger than that. That's half the margin of error. So times 1.96, and there it is right there. A 17. Wow, Blake, you are getting good at this. Blake, more points in the chat. Blake, you're becoming a pro at this. Blake has found that the margin of error is 17.89%, and so it wants it as a decimal. So we go right here to the center of 0.50 plus that. There it is, 0.6789, so it rounds up. And then subtract that, 0.50 minus the margin of error, and 321 right there to 3 decimals. There we go. Is that right, Blake, right there? Can we go over 2C? Yeah, of course. Explain what this interval means in context. I am 95% confident that the true proportion of mislabeled seafood packages is contained in the interval blank to blank. One is 95% confident that between blank to blank, purchase for the study. No. One is 95% confident that between, and then we have to multiply here, 32.1% to 67.9% of all red snapper seafood sold in food stores in these restaurants is not the actual label. Did we do it? We did it. Really good question. Where can I find the Stat 1 project instructions? I can't find it. They are loading up tomorrow. And great job, Blake, right there. I am 95% confident. Tomorrow, Tara, great work, and we will be covering that during office hours. Simone has the next question here with some 320, asking about how to interpret things. Unpinned message right there. Great work. Excellent job. Let's do it. And Simone was wondering about... Hey, we should be able to do it. Oh, wait. We might be able to do office hours tomorrow. Maybe. Might be a busy day. How to interpret total number of donations and age in multiple logistic regression. So interpretations in multiple logistic regression. So interpretations in multiple logistic. Was 320. BS 320. Here we go. Let's do it. So we need to do some interpretations in multiple logistic regression. So Meath, this is going to be some very important stuff for what's coming up. When we do logistic regression, this is a huge thing. I'll show you what logistic regression looks like. You ready? Logistic regression looks the following way. GLM. What's the first? What do you notice right here? What do you notice immediately about logistic that's a little bit different right there to start? What do you notice? There's the GLM. What do you notice about that? What do you notice about that right there? What do you notice immediately? Like, ooh, wait a minute. What do you notice? The categorical Y variable. Categorical Y variable. So logistic regression predicts a categorical Y. Logistic regression predicts a categorical Y. And then we have to add in one more thing. Family equals binomial. Binomial means it's a two-level, like bi meaning two, and nomial meaning nominal. So we have a two-level categorical we're predicting. And now take a look at the model. It's no longer a what model. The model is no longer a what. The model is no longer a what. It's actually called a sigmoidal curve. So this is the sigmoidal curve. We'll be doing this the week after Thanksgiving. We'll be doing logistic, I believe. So this will be the kind of last bits we do. It's no longer a linear curve. It's a sigmoidal curve. So what we have right here, do you think height is good at predicting if somebody is male or not? Do you think the X variable height is a statistically significant variable in predicting if somebody is male or not male? Do you think height is statistically significant? Because we're trying to predict the probability. I would say definitely, yeah. Height's, I'm not saying you know someone is male because of their height, but you say, oh, my friend's 6'5". You say, how is he? And they say, no, her. And you say, oh, I'm sorry, didn't know. But it's more likely, right? If somebody is taller, say it with me, it's what they are male. And it doesn't mean they are. I have friends of all different heights. My wife is about as tall as I am. She's like 5'10". That's pretty, yeah, she's kind of close to my height. 6'3", 5'10". She might be 5'11" for all I know. But they are more, well, they are taller. So if they are taller, they are taller. If they are taller, they are what? You basically said it. If they are taller, they are more likely to be what? Mm-hmm. Mm-hmm. And it doesn't mean they are. It just means they're more likely. It's just like, it's almost like we would say here, two people who differ in their height by 1 inch, the person who is taller, like if I were to go here to this data, and if I were to take person at height 67 inches, right about here, and person at height 68 inches, so we have person A and person B, and they differ by 1 unit of their height, the person who is taller is more likely to be male. Let's hear that again. Two individuals who differ in their height by 1 inch. It's simple, so we don't have to say otherwise identical. Two people who differ in their height by 1 inch, the person who is taller is more likely to be male. Does that make sense? But let's change the variable. Sorry, guys. I didn't help you out on this one. You'll see in a moment. Two people who differ in their GPA by 1 point. Interpret this for me, Meet. This will be on the final, things like this. Two people who differ in their GPA by 1 point, the person with the higher GPA is what? And look at the graphic over there on the side. Two people who differ in their GPA by 1 point, the person with the higher GPA. So you can see here you got person with a 0 GPA and person with a 1, person with a 2, person with 3, person with 4. Two people who differ in their GPA by 1 point, the person with the higher GPA is what? Two people who differ in their GPA by 1 point. Two individuals who differ in their GPA by 1 point, the person with the higher GPA is less like. That is, you just literally did a interpretation of logistic regression. And you know what you don't cite in logistic? You do not actually cite the coefficient, because the sigmoidal curve, the S-shaped curve, is not a constant bend. Notice, especially in the previous one, that down here the differences are very small, so you do not cite the coefficient. The coefficient only tells you if it's sigmoidal up, like this one goes up, or it's sigmoidal down, which would decrease the probability of the level of interest. The level of interest being the last alphabetical, i.e. male comes after female. So we are predicting the probability of male, level of interest, the one we are interested in predicting, and it's completely arbitrary just based on last alphabetical. How are we doing on Meath on this? Does that make sense? And Simone, and now I'm going to put in multiple regression right here and do some pretty craziness with it. But how does that make sense for the interpretations? It's just you interpret more or less likely to be the level of interest for the thing we're thinking about. And remember, logistic is for categorical, and we predict probabilities, as you can see by the y-axis. But now let's add in a little bit extra right here. We're going to add in weight, height, and handedness, and desired weight. So we can't really visualize it anymore, but let's take a look. Now, pretty much all of these coefficients are positive. Pretty much all of them are positive. But now when we say two individuals, when we interpret height right here, what do we have to say? Two individuals who are what? Because this is multiple. Since this is multiple, we have to acknowledge what about the two individuals. So I'm going to interpret height right here. Two individuals, and since it's multiple, who are otherwise identical. You could say it for the simple, but it doesn't really make sense because there's no other x's. So in the simple world, as Meath is pointing out right here, there's no other x's to say they're identical on. We have to go down here and say two individuals who are otherwise identical because they share the same qualities of other x's. Two individuals who are otherwise identical, but they differ in height by 1 inch. Finish the sentence right there, Meath. So I'll say the start of it. Two individuals who are otherwise identical, but they differ in height by 1 inch. The individual who is what is what? Remember, it's a positive coefficient. So if we saw some visualization, the visualization would look like this. Positive coefficient means more likely level of interest. So you have to top at the level of interest. So you have to know what that is. It's the last alphabetical. So two individuals who are otherwise identical but differ in their height by 1 inch. The individual who is what is what? I'll repeat again here. Two individuals who are otherwise identical but differ in their height by 1 inch. The individual who is taller is more likely to be male. It's literally it. Now, this actually breaks into something we've kind of started, which you've seen. Handedness is what is called an indicator variable. So we'll be going over this a lot today. Handedness is an indicator variable. So that means handedness was a what in the original data set. Being an indicator variable in the data set means handedness is a what kind of variable. So handedness itself is a what kind of variable. Just like what kind of variable is handedness? It's categorical. So categorical variables make what are called indicator variables. Got those cats in the chat. And what level of handedness do you not see in the output? So look at the output right here, and this is very important for today's lecture. What level of handedness do you not see? What level of handedness do you not see? You can just abbreviate it if you want. It's a long thing to write. We don't see ambidextrous. So ambidextrous is what is called the reference level. The reference level is what we compare things to. So we would say right here, so I'll give you this one here, and great job, Juliana, right there. So the reference level is the one we compare things to. So we would say two people who are otherwise identical, but one of them is ambidextrous, so that we're going to compare to that, and the other one is left-handed. The person who is left-handed, positive coefficient. The person who is left-handed is what? Two people who are otherwise identical, but one is ambidextrous, because we're referring to that, we're comparing to it. Two people who are otherwise identical, multiple regression, but one is ambidextrous and the other is left-handed. The person who is left-handed is what? Positive coefficient. What does that mean? What does the positive coefficient mean? Two people who are otherwise identical, but one is ambidextrous and one is left-handed. The person who is left-handed, person who is left-handed, because it refers to this one, is what? Is more likely to be male. More. Not that they will be male, just more likely. Because think about this. These two people down here, if you have two people and one person is 55 inches tall, another one's 56 inches tall, what would you predict for these people? So you have one person, person A is 55 inches tall, person B is 56 inches tall. What would you predict for those people? Here's their probabilities of male. What would you predict for them? And these coefficients do not talk about a percent difference because it's not constant. B is more likely to be male than A exactly. And we'd actually predict both are not male because this is at the point at which we would predict male above 50-50. So at about this height right here, which is maybe about 67.8, we would predict somebody is male. And that doesn't mean they are. It's just the predicted value from this model. And so that is where we would start predicting male. And if you are taller in this simple model right here, you are more likely. So the coefficient does not talk about the difference in probabilities because the difference in probabilities are not constant. It's just if it's positive, it's sigmoidal up, and if it's negative, it's sigmoidal down. So interpret, and this is weird, but interpret this coefficient right here, which is very statistically significant. Interpret that coefficient. This is probably the last, and then we'll do Meet's question here. Interpret that coefficient right there. And if you can interpret that coefficient, you really have interpretations in Logistic down, which is a good portion of the final. Not a big portion, but you have to write them. So if you can interpret that coefficient, you're doing well. So this is Logistic regression, where we are predicting the probability of somebody being male, because male is the last right here level of a two-level female-male variable. And so we are predicting probability of male. So how would it start? Two individuals. People are probably writing right now. Two individuals who are otherwise identical, but they differ in their weight. Two individuals who are otherwise identical, but they differ in their weight by... If you have this down, Meet, you're doing really well. And then we'll do the 2B I think you wondered about. Let me go grab that here while you write this, if you're writing it. I want to put that question again. 2C. 2C, you said 2C. Two individuals who differ in weight by 1 pound but are otherwise identical. Be careful. So and I'm so glad we did this right here. So what are we predicting right here? The Y variable of interest is probability of male, right? Or predicting if somebody's male, right? So in Logistic, and this is a huge note to take, Meet, right here, never mention the coefficients. So this is a huge note. Never, this is like, as long if you see you're doing Logistic, don't mention the coefficient. The only thing that matters in Logistic is the what of the coefficient. The only thing that matters in Logistic is the what of the coefficient. The only thing that matters, so you see this is going down, this is going up, the sign of the coefficient. That's the only thing that matters. So you ready? So get ready. Here's the interpretation. two individuals who are otherwise identical but differ in their weight by 1 pound, the person who weighs more is less likely to be male. So it decreases the probability of level of interest. So we don't mention the value of it, we only mention the sign of it. So I'll repeat that again here. Two individuals who are otherwise identical but differ in their weight by 1 pound, the person who weighs more is less likely to be male. But think about this also. Two individuals who are otherwise identical but differ in their desired weight by 1 pound, the person who wants to weigh more is more likely to be male, which kind of makes sense right there. Remember, this is a multiple regression, which I think Simone's asking about right there. The multiple regression says, do these variables bring with them new information in the multiple model? Because in a simple model, I'm pretty certain that in the simple model, that weight by itself would probably have a positive coefficient, that people who weigh more are going to be more likely to be male. But remember, this is, and the sign determines more or less likely. Simone says, after accounting for, Emily's got a question too. I'll see here. Simone says, after accounting for differences in total number of donations, does the probability of donating increase or decrease as donations gets older? So what would you look at right there to see if the probability increases or decreases, Meet? To know if after accounting for the variation for height, handedness, and desired weight, does the probability of somebody being male increase or decrease based on their weight? After accounting for the variation in height, handedness, and desired weight, does the probability increase or decrease depending on somebody's weight right there? What would you look at? So after accounting for the variability in height, handedness, and desired weight, it would decrease, right? And what you want to look at right there is the what, which is the main important thing of it. So coefficient is what? Like not lower, yes. I kind of know what you're saying with that. It's going to decrease the probability of the level of interest because the coefficient is changed lower a little bit. Like the coefficient is what, which means it will decrease the probability of the level of interest. So after accounting for the other variables, which means we're in a multiple model. So after accounting for the other variables, the people's differences in weight, people who weigh more are going to be less likely to be male because the coefficient is negative. Exactly. Lower might mean that it's smaller. It's not that it's smaller, it's that it's negative, that the probability decreases. Now, this is not the same model, but it does show a sigmoidal down. This is when we have negative relationships. So Simone, I hope that helps right there. The coefficient sign is going to determine whether or not something is increasing or decreasing the level of interest. Emily says, I know you covered a little bit ago, but I was wondering how you got the Z-squared from the David M. Lane for the consumer advocacy question. Good question. What % confidence does it say? And then, Meath, we're going to do your question here next. What % confidence does it say for you, Emily? So what % confidence does yours say to have? It says blank % confidence. So when you go to the David M. Lane, you want to click the second button for value from an area. So we're going to shade a certain percentage of the area. And then you want to put in the % area. And then remember that a confidence interval is the in-between. A confidence interval is the in-between shading. I'm looking for good questions, Emily, right there. So this is the 98% confidence Z-score. Make sure it is the second button right here. And the link's in the chat for David M. Lane. Then click the between. We love some David M. Lane. Then click the between and change the value accordingly to whichever one it says, and that'll give you the Z-score. The Z-score is the %, or we're using it this way to get the confidence interval Z-score for the shading of the middle blank %. Frogs in the chat. You're welcome. So Emily, I hope that helps out. Tell me if you want what the % confidence is, and I can tell you the Z-score via looking it up in the applet or checking it right here. And Meet, let's go to your question. Thank you, Meet, so much. And that gives you a head start on the info right there. Awesome, Simone. Glad that helped out. Let's see, 5703, BS 320, multiple regression assignment 2C. Let's go look at some 2C. You're welcome. Oh, no worries. Yeah, tell me when you find it, and I'll mention it here in the chat. Multiple regression. And then doing some logistic. Okay. You got the trouble in the interpretation? Do you have it down? Two individuals differ by, it's, let me know how your interpretation is working. 95, 1.96. You should have 1.96 as your z-score. Chapter. Oh, and didn't someone want some chapter 14? I think Julia came by and wanted some chapter 14. Which one? Chapter 14 is very similar. We might have time to do a chapter 14. To see. Yeah, which one do you want to do, Blake? Okay. Fit a model predicting demand from the two variables right here, including the interaction, but omitting the offensive row. So make sure you find the offensive row right here. The offensive row is a row that is a combination. Shout outs to Alexander. I'll show you what we can do right here. The library psych has a pairs plot function. Is it pairs plot? Pairs panel, there it is. And we're using the bike data, I think. So ex3 bike. ex4 bike. Shouts to Alexander right there. I got that part. And so I believe the offensive row is that one. And you can see some high multicollinearity. So really great graphic right here showing the histograms, which are the univariate visualization of a quantitative variable. The correlation coefficients right here for each of the pairwise comparisons between like demand and average temperature. The linear and nonlinear relationship. Meet, do you like this right here with average temp and effective average temp? Remember, we're trying to predict demand. What's going on right here with these two X's, which it's like, yeah, this is maybe not something I like. You say, whoa, that's great. Look at that relationship. No, that's the X's explain the X's, which is multicollinearity. So this is not good. 99, which if we look at it as an R squared, if we can times it right here, it's going to be like 98%, which is going to lead to really high variance inflation factor. Just looking at this briefly right here, which Meath, I think you've already looked at, but we'll just look at it. Explaining using all the variables right here, and we look at the variance inflation. So the variance inflation comes back ridiculous, and you could do a reverse calculation on this to basically see it, 1 over 1 minus R squared, and we're getting very similar numbers right there. I don't know why. Oh, this must be rounded up. It must have been something close to 99 that rounded up, like probably like 987 or something like that, and then it just rounded it to 2 decimals, and then yeah. So then if we were to put this into the formula, yeah, it's rounding it up, it looks like, with the 99. So, and I think those are the R's, not the R squareds. Yeah, they have to be with that. So this is not good. High multicollinearity. And then looking at this right here, the influence plot is going to tell us which values in these models are giving extreme influence. So think about this, Meath. If this is the universe, like right here's the whole universe, and we need to move to a new planet, how much of the terms of space that planets have on them, this planet over here basically what? Because the size of the circle is the size of the influence in an influence plot. So the size of the circle, it's kind of, well, it's an outlier with huge leverage. So it's an outlier, it has huge influence. Yeah. The size of the circle denotes the size of the influence. The deleted studentized residual would tell us that it's a bit of an outlier from the model, because that's when we delete its influence, and we delete it from the model, removing its influence, and then we look at its residual. So this point is like, this data observation is like insane. How could I go? What should I add to EX4 bike to go look at this? What could I add to like look within and grab this row? What could I grab? And I think you can actually take Yelp, Meath, you are a pro. And look at this, Meath, right here. We can take and run it with the following code right here. So I stored the output of the influence plot into an object, and then you can take the leverage points right there and just put those rows. So all this is doing right here is running it with this and then showing me that row. So once again, this code right here is just taking and doing, I wonder. No, it doesn't like it. You could do it this way if you do that. Would it make the plot also? Maybe not. Let's find out. Oh, it does. Well, that's a much better way to do it. So watch this. it'd be a little tougher. Yeah, so you can just put it inside of there and call from the list it creates, the leverage, and then just report it. So let me drop that in the chat. Probably a better way to run it, and then you just report the rows right there. So just put your data frame right there. Give me 2 seconds. Watch this, Meath. Let's go here to fun and call it influence plot plus. And it's going to take data. And right there's that. And so this will just be your data. And that might do it. Okay. And so now if we run influence plot plus and we do ex4 bike, it's going to like it. There it is. So I just remade Dr. Petrie's function to influence plot plus, and it actually just reports the rows for you now. So now it's a new function, because I'm like, why go and do all that? It's just a function that does it for you. Why not? Just take what you have right here and say, well, someone's just going to insert the data and just plug the data right here and then run the code that we have, and then boom, answers. So a lot better, but you need to know what it's reporting to you. This is reporting to me that what? Observation what? What does this mean? That is what? In my data set, in my data, so we're going to remove this here in a second. In my data, the observation in row 337 is very unusual. So it's reporting these values. So it's saying this is a very unusual combination. And if you look at the pairs plot, it really boils down to the combination of average temperature and effective average temperature, because usually those values are very what to each other. This is answering other questions too, which you've maybe been doing, Meath. So usually the values of average temp and effective average temp are basically what to each other. They're really close usually. They're very linearly related. We saw this in the pairs plot earlier, way earlier with the pairs. They're usually very linearly related. So you can look at the effective average temp, and that's this point right here. So that is the observation right there, 337. And so that is a bit of a weird one. That is something going on right there. So weirdness. Yeah, I could probably do some even better plots of this. We can compare 337 to summary to find out how unusual. Exactly, and that's what you need to do right here. So if you look at the summary of the EX4 bike, you can get an idea of what's going on right here. So we're going to make that full screen. And great job, Meath, working on this. So there's the summary. There's the point itself. And when you look at its demand, which that's not what we're looking at, demand does not control leverage because demand is not a what. Demand does not control leverage because demand is not a what. One letter is all that's needed. Demand is not controlling of leverage because demand is not a what. Leverage is how unusual things are in their combinations of their whatses. How far you are away from the means of the whatses. So demand plays no role in leverage. It will in delete a student dies residual, though, which is how far we are away after removing its influence. So demand does not control leverage because demand is not an X. Leverage is only your distance from the mean of the X's. And we are predicting demand, so that will go to the residual. So demand is going to play a role in how far our prediction is. Great job, Blake, right there. Yep. The X's are what control leverage. Blake, 10,000 points. Love that you're chiming in right here. Keep up those answers. So what do you notice about average temp right here? It's in the top what? So right there, Q3, some stat tool 1. Demand is in the top, or average temp is in the what? Average temp is in the what? Top 75%. But remember, usually these two are highly correlated. Usually these are highly correlated. So average temp is in the top 75%. But effective average temp is in the what? Effective average temp, which usually they're linearly correlated with each other. So it's kind of weird that average temp is so high and effective average temp is so low. And so we see here that the effective average temp is in the bottom 25%. So that's unusual in its combination of X's. Like that's very unusual given how the X's have a certain relationship. This is leading to its high leverage, which is how unusual it is in the X's. That's probably the largest component. Average wind speed is in the top, right at the top 25%, top 25%, 70th percentile. And this is closer to the median. So it's really probably its unusual nature in this. So we can remove this data point right here in a model. We just go right here for our data and remove row 337 from the data set to redo it. So let's go ahead here and make a new model. We'll call it model 2 from a linear model predicting demand from, and data is going to equal, what variables did it want? It said an interaction between average temp and average wind speed. So we need the interaction between average temp and average wind speed. And there we go. And now we go to visualize model. I think we can visualize this one. No, M2 not found. Oh, we need a comma. Object M2 not found. Why? Oh. We had a comma. So does it remove the row permanently or just from this model? You could remove it permanently, but it's just from this model. It still exists right here, but when we run the data with this will be one less. So you could say new bike is this, and then you could have data equals new bike. And so now with data equals new bike, you'll see new bike right here has one less observation than EX4 bike. So you could technically remove it and create a new data set with it removed. And you could say no outlier or no extreme value, no extreme bike, something like that might be better to call it. And then store it right there, and you get the same thing and too large for the margins for the figure. Does that make sense, Meath, right there? That point has been removed from the data if we store it, but if we run it with the following, it's just removing it temporarily. Just when we run this right here, it has it removed. It's not permanently removed till we write an object with it permanently removed. The question says, model all two interactions. See the interactions with many equals true. Okay, see interactions with many equal true. And M2, many equal true. There we go. And we need to make this way bigger. Okay. So when you look at this right here, the interaction doesn't appear to be that strong. It's not that strong of an interaction. Very hard to interpret this one. Let's look at the coefficient of the interaction. Okay, the coefficient of the interaction is positive. So if we interpret this, what does it want us to do? You guys want to see right here. Include the interaction. Examine the summary and visualize the interaction. Oh, is it statistically significant? Check a question on a polymodel. We could look at that, Abby, too. So is the interaction statistically significant? And the lines were pretty parallel right here. Is the interaction statistically significant, Meath? It's not. And so really, it doesn't matter. It's not that big of a deal. It's not that important. But when average wind speed is higher, the effect of average temperature is more significant. The line is more steep. We'd really want to see a stronger interaction here to better understand interactions. So the stronger the interaction, the more perpendicular the lines are. So the interaction here is pretty weak. It's not statistically significant, and so it doesn't bring with it new information. Probably starting to get some multicollinearity right here in the model. Yeah, there's a pretty high degree of multicollinearity at this point. Interactions usually do that. Abby, you're wondering about check regression on a polymodel. So if we were to make this a polynomial model right here, the polynomial model could be made with the following. Is this correct? I think that'll do it. I think so. And great job, Meath, kind of coding right there. I like that. Probably the easiest thing to do is to just multiply them like this. But Meath's pointing out you could put them in a parentheses and then raise the parentheses to do the interactions between all the variables. We should get the exact same model right there, and we should get the exact same output. And there you go, Meath. Same output. Yeah, when you put the extra equals true, so if you do check regression, and you do this, and you do extra equals true, and you're getting a spinning wheel, go ahead and hit enter down here on the bottom. So with the extra equals true, so Abby, does that help right there? Go ahead and hit enter down there on the bottom, and it'll give you the extra plots. And these are the individual variable plots right there with the extra equals true. You might need to remove that when you knit. Just let me know if you have problems, but You want to then hit enter down here on the bottom. It's probably prompting you in the bottom console. Does that help out? Help out, Abby, right there? We got class in 12 minutes, but did that fix the issue right there, Abby, with the extra equals true? Yay, awesome. Thank you for swinging by and asking. Just remember, anytime you have a problem, just let us know, because little things like that can just be like, well, it's broken. What's going on? And the interpretations are still the same. How many conditions do we fail right here? You would still look at this and think, how many conditions do we fail? So let's say this is your output for your model. Still the same sort of things going on. How many do we fail right here? How many tests are failed? So if you know how to do check regression, same sort of technique that we've always been doing on this, how many conditions do we fail? Ooh, careful. Very close. Normality is failed, and then there's one other. There is two. One's just barely close. Exactly, yeah, just barely there. Then this means we couldn't run this test. This isn't failed. It's just we didn't have enough duplicates to run it. You have to have repeat values to run your x's to see if the model is going through it linearly. So that just means you couldn't run it. So you could look at the overall plot to see the linearity of it. And so let's see. Looks pretty good. The big one's the normality of residuals. If I ask my 7-year-old nephew to draw a straight line, do you think I'd tell him he did an okay job? What do you think right here? I asked him to draw a straight line. I mean, I'm not giving him a gold star for this, but which one, Ivana? We might not have enough time because I think we start class in 10 minutes. Which one are you wondering about homework-wise? I don't think we have enough time. When is that due? Is it due next week? Hopefully it is. Let me go look at the due dates on that. I would say this isn't horrible. It fails. It's our greatest concern. The linearity looks to be all right. The linearity of the x's looks to be all right too, even though average temp fails. Not the end of the world on that. Chapter 14 homework is due the 22nd. So good news right there, because we are starting class soon. The 22nd is Tuesday next week. It is due next week. Good stuff right there. And does that make sense, Abby, right there? What do I interpret when looking at the p-values for the poly? It looks like there's some problems with the fit of those right there. It's finding the critical value. Ooh, we can do that real quick. So is it asking for the T critical value, Ivana? We'll do that really quick. And so, Abby, that means you fail some of the tests that maybe there's some issues with the fit. So maybe there's some issues with some of the fits. Like maybe some of them don't have good fits. So if the p-values are low for those, then I would say maybe some of those have bad fits. So here we go, Ivana. We're going to speed run this right here. You're welcome. Thank you so much. Thank you, everyone. I started a tiny bit late. I was getting some work done for some of the many things. And I really appreciate no one being like, what, Brian? Brian, you're late. So here's the T-curve right here. You would look at all of them just to see how it's doing. And you might say some of the conditions are failed or blank amount of the conditions are failed for the fit of the polynomials. So you would probably just say, you'll use the orders you have, and then you'll just look across and say, like, we fail, probably fail a bunch of the conditions. But then you might say, overall, the model looks to not, then you'll look at the plots. And you might say, overall, the plots, if they look like this right here, what am I looking for in these plots for linearity? I'm looking for signs of what, Abby? If I'm checking the linearity and I'm looking at these extra plots, I'm looking for signs. And I mean, I see it a little bit here. I see it a little bit here. Okay, I see why this is a little bit angry. But I don't know. That's not horrible. Oh, not the equal spread. So the equal spread's the equal spread. The equal spread will be the equal spread right here, which is checked for... sorry, Blake. The equal spread will be checked right here for equal spread. If you're looking at this right here, you're looking at the what? You're looking for signs of what? I'm whatting my mouse right now around the line. I'm whatting... It starts with a C. I'm whatting my mouse around the line right now. I'm whatting my mouse around the line. Curving, exactly. So when you look at the extra equals true, you're looking for curvature. So if the line is going through the data well, that's what each of these plots are checking right here for the linearity of average temp. All of this right here, all of these are good except for this one, which has a tiny bit of curvature. It's not the end of the world. The equal spread would be looked at via this p-value, which is good, so we don't even have to worry about the equal spread. It is the same plot for the overall, and you could look at the overall model here, even though we can't calculate a p-value right there. To Ivana's question right there, and thank you, was Ivana asking? To Ivana's question, for finding the critical value, if you put those values in the chat really quick, I can find it for you. You want to go to the between and go to the t-applet, and then you want to put in the degrees of freedom. Like if it says 26 degrees of freedom, then you want to put in the percent confidence, and that'll give you the T critical value right here. So if it's asking for the critical T value, you want to put in your degrees of freedom, which is sample size -1. There we go, 99% confidence with your first answer is going to be this right here, 3.055. You're welcome, Abby. So 3.055, enter in your degrees of freedom into the T-applet, and then enter in the percent confident, but make sure you're doing the between, which graphs the area between. Does that make sense, Ivana, right here? This site right here is going to be your pro way of solving them. And make sure you're on the between to do a confidence roll because it's percent between for confidence rolls. Make sure to enter in the degrees of freedom, which are sample size -1. And then the T statistic will be calculated for you right here, which is the critical value T used to create the interval. In the following equation, we'll write it down real quick, and then we got to do class. The equation is that you're using y bar plus or minus T star, and that's what we're finding with n-1 degrees of freedom, S over square root of n. It is having you calculate this, the degrees of n-1, and you're welcome, Ivana. Great work. Bye for now, everyone. Bye. I'm going to go grab a snack.